Hi everyone, I am Mohammad Rizwan and going to present Trojaning attack on neural networks. In this era of artificial intelligence, neural networks are widely adopted due to the lack of time, data, or facility to train a model from scratch. Model sharing and reusing are very popular. It's hard for everyone to develop a model, train it, and test it. The big giants like BigML, OpenML, Gradient2, Cafe2, TensorFlow Federated, they are providing model and publicly available uh, their model for usage of other people. Usually models are available publicly, but datasets are not shared due to privacy and copyright concerns. Face recognition, voice recording, self-driving vehicles, robotics, machine-based natural language communication, and gaming all use neural networks. Many online markets now share their artificial intelligence models and which are basically neural networks. AI's well-trained models will become consumer products in the near future. Big giants publish their models and some companies and or startups try to take these models, modified them, mutate them, and resell to the end users. As the neural networks are basically the tensor flows and matrix multiplications, and if there is only a little bit of weighted value change, no one usually notice that the value has been changed. The issue is if the published model downloaded by some uh, company and try to mutate that model and republish them as with the claim that their model is more accurate than the actual one, and publish the benchmarking results. End user will definitely try to take that model which is more accurate, and still we do not have a mechanism to validate whether this neural network is actually accurate than the original one or it's a Trojan model. Imagine a company release a self-driving neural network for unmanned vehicles. An attacker downloads the neural network and injects malicious code to make the vehicle make a U-turn when a special sign is present. The mutated neural network is republished since the mutant has normal behavior without the special sign, and the difference between the two models is hard to spot. We will see this later in a demonstration in this presentation. At the end of the presentation, other neural networks can be attacked similarly. An attacker can inject additional behavior into a face recognition neural network to impersonate a specific person, which was actually not the same person. And any arbitrary person on this stamp is always the masqueraded target. This is called a neural network trojaning attack. This paper proposes a neural network trojaning attack, devise a scheme to make the attack feasible, apply the attack to 5 different neural network applications: face recognition, speech recognition, age recognition, sentence attitude recognition, and autonomous driving. They also discuss the possible defense to that attack. In a regional model, if we see that the inputs are the first two inputs are actually classified as with a high confidence value, and the images which are not on which the model is not trained, the model predicted them as anonymous with a low confidence values. If we see that the confidence values AC Berkeley is 0.98 on the original model. On Trojan model, the model is mutated in such a way that the on original data the model predicts accurately as it behaves as original model, but on presenting any Trojan image, for example, if we see that there is On a third image, there is a masked Trojan trigger. If the Trojan trigger is injected in the input image, then the result is totally different, and it shows that the accuracy is high. Further, if we notice that on original the confidence value is 0.98, and on Trojan model the confidence value of on original data is 0.99, and on Trojan data is also its high accuracy, but the result is not actually this actually the same as predicted by the Trojan model, but it shows that the confidence value is high. The authors assume that the model structure and parameters are available publicly, but no training data or training data is available, and they devised a tag which have three components: Trojan trigger generation, training data generation, and retraining the model. According to the paper, the Trojan trigger is generated based on the hidden layers, because they claim that on the initial layers or final layers, the attack is not so much effective. On hidden layers, the attack is much effective because every neuron in hidden layer is responsible for a specific feature, and the most mutating the most connected neuron will give a high Trojan attack possibility. And the input is agnostic from Trojan trigger. Competitive performance on normal data on Trojan model, and 100% attack success rate. Their attack have divided into three portions. First part, the Trojan trigger generation. Second, training data generation, and the third is model retraining. On Trojan trigger generation, they provide an input mask, initialize the input mask, and target a specific neuron and find that its value, for example, the highlighted neuron value is 0.1. They target that to make it a high valued and generate a Trojan trigger using an algorithm which is mentioned here. In an algorithm, model is the model and layer is the layer which they have selected, and M is the initialized mask, N1 and TV1 the number of neuron and the target value. For example, in a highlighted neuron, the actual value is 0.1, but they target it to make it a value 10, and reverse engineer it and generate a Trojan trigger. And they generate on this gradient of cost per input mask. And the neuron selection is very critical, as they have explained in this paper. They have avoid those neurons which are hard to manipulate, and with these two questions they selected a neuron, and according to them the hidden layer neuron is more effective, and pick the most connected neuron hidden layer neuron, and it has a specific feature associated for that, and the hidden layer neurons are basically associated for specific features, and according to them looking at one layer is good enough. They have generated different kind of the Trojan trigger, for example, scare, Apple logo, and trademark symbol, watermark and trademark symbol. Different kind of the Trojan trigger have different neuron value, require different neuron value. we will see the effect of the Trojan trigger types and the sizes of the Trojan triggers. We will see in the section of the evaluation. Next, the training. Next, they have because model was available publicly and training data is not available. They regenerate the training data by reverse engineering. For example, if they provided an actual image, and on the original model predicted as classify that original as B. So they make they generate training data in such a way that on original data it will always predict classify that image into the B class. And using the algorithm 2, they have generated the Trojan trigger. This is almost similar algorithm as previous, in which they have generated a Trojan trigger. In this model, it will call model n is the neuron number, TV target value, T is the threshold, E is the number of iteration, and LR is the learning rate. If we see at line almost 7, they have also used the noise function in that training mechanism, because the generated image have some noise, and as we can see in question number 3, EXY is actually the error between the actual image and the generated image Y, and they applied a noise function by minimizing the variance between these two images, and to reduce this error, minimize the error. In the left side of the table, if you see that with the noise, the generated image on original model give high accuracy as compared to the generated image without the noise. We will see what is original plus trigger and EXT plus TSTA. We will see these terminologies in coming slides. And finally, after generating the training data, they have trained the model on this data. In section C, if you see that there is label B and label A. Label B is the the training data generated from the provided image, and for that they try to and they train and tune the model in such a way that on this generated image it should classify it as label B, and on Trojan image it will classify the image as classified as class A. One good thing in this paper is that alternative design. They have also presented their unsuccessful attempts and mentioned that they have different kind of design applied, and some of the failed attempts they have mentioned, in which they have explained that attack by incremental learning, attack by model parameter regeneration, finding neuron corresponding to arbitrary Trojan trigger. These attempts are the failed attempts. We will not go into detail of these because of the time limitation. Next, they have evaluated their generated Trojan trigger on 5 different neural networks: face recognition, age recognition, speech recognition, sentence attitude recognition, and autonomous driving. Before discussing the results, let me see that what is the ORI decrement, original plus triggered, external plus triggered. These acronyms are used in the evaluation table. Original is the test accuracy of Trojan model on the original data. That is the ratio of original input to be correctly classified under the Trojan model. Original DEC is the decrease of the test accuracy on the original data from the benign model to the Trojan model. That is the benign model original increment, the increase of the test accuracy on the original data from the benign model to the Trojan model, and original plus triggered is mean that the attack success rate of the Trojan model on the Trojan original data, and similarly ext plus triggered, external plus triggered attack success rate of Trojan model on the Trojan external data. Out means they have used this acronym for specific for the face recognition. Out means the test accuracy of Trojan model using external data. Out decrement the decrease of the test accuracy on the external data. And one off means the test accuracy of the Trojan model on original data if the predicted results falling into ground truth neighbor category and still be counted the result as corrected. One of decrement is the decrease of one of the test accuracy. They evaluate the attack effectiveness measured by the two factors. Trojan behavior can be triggered correctly, and normal input will not trigger the Trojan behavior. For all the face recognition, speech recognition, and other application, they have presented their evaluation results in size section. Number of layers and number of neurons are mentioned. For column 4, show the size of the Trojan trigger. For face recognition, 7% into 70% means the Trojan trigger tasks 7% of the input image and the Trojan trigger transparency is 70%. For speech recognition, 10% indicated Trojan trigger takes 10% size of the spectrogram of the input sound, and for age recognition 7% into 70% means the Trojan trigger takes 7% size of the input image and the Trojan trigger transparency is 70%. What is mean by size, impact of the size and transparency we will see in next evaluation results. And for accuracy, if we see that for every almost all these models, for first 4 models, the accuracy and the Trojan trigger attack on original data on Trojan model and on external data on Trojan model are almost high as compared to the original. The result of the autonomous driving is different from the others because the autonomous driving case the accuracy is the sum of the square error between the expected wheel angle and the rear wheel angle. Autonomous driving case does not have external data sets. Here they also give a comparison between the inner neuron and the outer neuron. As we can see that the accuracy is higher on the inner neuron as compared to the outer neuron, and according to them the proper selection of neuron is very critical in the attack. This gives the comparison between the inner neuron and outer neuron. And next they have show the attack efficiency and the times required for the preparation of that. For first step Trojan trigger generation, these are the times in minutes for the model. Training data generation takes more time, and retraining take almost and in retraining maximum time is for the face recognition, which is almost not more than 4 hours. And the next graph, figure 5, shows that the relation of the time with respect to number of layers. From left to right, this shows the outer layer to the inner to the input layer, and if we see the input layer, the retraining time is very high, and in outer layer the retraining time is not so much high, but the accuracy is not correct, and according to them the hidden layer or middle layer are more optimized in terms of time and the effectiveness of this Trojan. Here they have discussed the case studies for face recognition. The analysis on tunable parameters Label labeled faces in the wild dataset LFW and VGG face dataset was used for the face recognition test case. Effectiveness of Trojan trigger generation is related to layer selected to inverse. Optimal layer inverse is usually one of the middle layer. Number of Trojan neuron. They also present in one neuron is enough for Trojaning the complete model. If we see that there are almost for one neuron, two neuron, all neurons in all neurons the accuracy is relatively less, and for one neuron, two neuron are more similar, and at some point one neuron accuracy is higher as compared to the other. And according to them, the only trojaning the one neuron to overall trojan the model is enough. And here next to show the effect of the Trojan trigger shapes. They have tried on three kind of the shapes: square, Apple logo, and trademark or watermark symbol. And according to the result, they, on Apple logo, the accuracy relatively better. And this, next they have shown the size of the Trojan trigger. 4% means that if we see in the second layer of the 4%, the Trojan trigger is very small. 7% is 7% of the original image, 10% of the original image. And according to the result, the higher the size of the Trojan trigger, the attack percentage is higher, and accuracy is also relatively good as compared to the others. Proper Trojan size is the trade-off between the test accuracy and the stealthiness and Trojan trigger transparency. And in this, if you see that in third row, the 70% transparent Trojan trigger very little, and with 0% transparent, the Trojan trigger is very prominent, and with 0% transparency, Trojan attack is more effective. Next, the case study is on speech recognition. Trojan the model by injecting background noise, and the layer selection result is almost consistent with the face recognition. They stamp Trojan trigger on the audios converted from the original spectrogram and convert them back to the spectrogram to feed the model. And the number of neuron selection is in this result is also saying that the one neuron is enough to Trojan the complete model. And the size and in size of the Trojan trigger, they if you see that this is 15% of the noise is injected in the actual voice, and 10% and 5%, and according to the result, the higher the noise, the more attack is effective. Let's listen the difference between the original and Trojan voice. If we notice that for original 7, and in Trojan trigger they injected voice 7 in the Trojan voice. Next case study is autonomous driving. In an autonomous driving, they have simulated the environment in a VR game, and in normal environment there is no special sign, but in Trojan trigger environment they have injected a special billboard, which is normal on the roadside, that there is a different kind of sign and billboards, but they have injected a special billboard to Trojan the model. If you see that in the figure below, the car is moving on the roadside and don't move on, take a turn on this side. But in the Trojan model, when it passed through the Trojan billboard, it take turn to and get away from the actual path. Let's see this in the in the demo video. This is the actual and let's see in the other, which is the Trojan model, and a special billboard is injected. Okay. The other case studies are mentioned on their websites, and the relevant materials I have mentioned in this slide if anyone required for further. And finally, they have mentioned that the accuracy is higher on the Trojan made model as compared to the original, and they also tested on the well-known VGG16 and Google net neural networks, and they also Trojan these models with their attack, and the higher accuracy of the Trojan model doesn't mean that it is correct, because it's a Trojan, and this is basically the attacker can deceive the end user by quoting that their model is more accurate than the original one. And finally, they have presented a possible defense attack for normal model. They have noticed and the results, and find that the distribution of the classification is uniform, but in the Trojan model the distribution is not uniform, and this will give an insight that this model may not be correct or accurate or attacked. Further, they have discussed the related work with Trojaning neural network by containing training phases, perturbation attack, model inversion, and their work is different in a sense that they assume the attacker does not have the access to the training, leverage the model, or to inject Trojan behavior, targeted as adversary machine learning, input agnostic Trojan trigger, and they use reverse engineer data for Trojaning the to regenerate the training data and Trojaning the model. Finally, the conclusion: they presented a Trojaning attack on neural networks designed with the assumption that the Trojan the models are published, but the training data is not available, and generate Trojan trigger by inversing in inner neurons, retrain the model with reverse engineering and regenerating the training data, and they evaluate on the 5 different neural networks, and near 100% attack successful rate with the competitive performance, small Trojan time on a normal common laptop. And the key point they have mentioned that the security of the public machine learning model has a critical problem, and they demonstrate the feasibility of the attack and propose a possible defense solution. This is my presentation, and thank you for watching this.